Kazuteru Miyazaki's presentation?
Yes, I'm here.
Thank you, Kazuteru. Are you ready to start your presentation?
Yes.
Yes. Go ahead.
I'm Kazuteru Miyazaki from Japan. Today, I'd like to present modeling of placebo effects in stochastic reward tasks by reinforcement learning. This is outline of my main points. Several studies in the computational psychiatry field focus on modeling diseases using reinforcement learning. This study aimed to model through reinforcement learning using real data of stochastic reward with regard to the placebo effect. We modeled the placebo effect using real data related to the non-invasive brain stimulation technique, NIBS, such as TDCS and TNIRS. The result of our method shows no difference with human data. This study uses the 29 healthy male data in this paper. First, the participants engaged in the baseline session, in which no intervention was made. The baseline session was followed by 2 balanced and active placebo sessions that were randomly ordered. They are expressed as A and B, corresponding to low and high uncertainty. The participants were assigned stochastic reward tasks with 3 levels of difficulty, 80-20%, 70-30%, 60 or 40% for each symbol pair, where 3 pairs of Chinese symbols, different ones for each session. The images in the first line, A to F, are shown in the practice session. The second line, Z to I, are in the baseline session. The third line, M to R, are in the low uncertainty. The fourth line, S to X, are in high uncertainty. The value in percent indicates the probability of receiving a reward. The probability getting a reward is constant in the experiment. The participants were asked to choose the stimulus with the highest reward probability from the symbol pairs. The tasks were composed of 6 blocks with 60 stimuli in each block. In A, low uncertainty, the participants were told they would receive a composed stimulation TDCS and TNIRS, a standard and effective intervention for improving cognition. In B, high uncertainty, the participants were told they would receive a TDCS intervention whose effectiveness had not yet been improved. Through the participant and data collector were uninformed, TNIRS were inactive. Therefore, the skin sensation induced by the stimulation was psychological equivalent in the 2 placebo sessions. When a participant chooses an image with a high probability of getting a reward, it is considered as a correct answer. For each participant, we calculate the average correct answer rate across all the 180 pairs of stimuli. The average values show that A or B have a higher correct answer rate than N. N is baseline session, which confirm the presence of the placebo effect. Focusing on the correct answer rate for each participant, it is possible to observe a variation in the difference in the correct answer rate in N, A, and B of each participant. Therefore, we not only model as an average value, but also the variation in the difference of each participant. We performed reinforcement learning executed with the symbol pair presented as a sensory input and the participant choice as an action. Reinforcement learning method uses were Q-learning and profit-sharing, where the evaluation value to be learned is denoted as the Q value. We initialize the Q value with the following 4 patterns: P00, P01, P10, and P11, where 1 means each part is corresponding to participant and placebo. The part that initialize according to change in the effect of the participant or placebo. For example, P01 means the Q value is not initialized when the participant changes. However, it is initialized when the effect of the change. This is a result of our experiment. There is not much difference between A, N, A, and B with any pattern. Therefore, we only use the result of P00 later. Though the algorithm learns by reward, the probability of the reward is always constant. Therefore, the participant may generate different results with N, A, and B depending on the atmosphere at the moment. However, reinforcement learning learns without being influenced by such factors. The data of human participants show a unique pattern for each participant. Therefore, next, we model it using profit sharing. The kind of modeling was achieved by adjusting the Q-learning values, temperature parameters such of Boltzmann selections. However, regarding the data using in this study, when the action was selected by Boltzmann selection, the correct answer rate dropped sharply. Therefore, we decide to fit the model with other than Boltzmann selection. We set the parameter ikichi that works as threshold for action selection. This indicated that an action is only considered if it exceeds ikichi. It is possible to produce various behaviors by changing ikichi. We ikichi assumed 0 and 1, 10, 100 and compared them. It is also possible that some participants have better memories than the others. We had the idea of introducing the kyoku 0.0 from 1.0, a parameter that determines the probability of blocking a choice with a certain probability before the final output. If ikichi equals 1.0, the action is output as per the participant choice. Nevertheless, as the value becomes closer to 0.0, the probability that the action output is in accordance with the choice decreases. In addition, a certain known as sabun, which is used to calculate the difference in the Q value between two choices. If the value when the Q value of choice B is subtracted from the Q value of choice A is larger than 7, the action prompted by the Q value of choice A is considered. Sabun assumed 0 and 10, 100 and compared them. Lastly, it is possible to set coffee as another parameter as sharing. Since the value equal to or smaller than coffee equals 0.5 satisfy the rationality theorem of profit sharing. We attempt to fit the model by changing coffees with this range. Therefore, model fitting is attempted by changing the four parameters, such that ikichi, kyoku, sabun, and coffee. The model result by profit sharing related to the result previously. Table 2 P00 and best match indicate the model error, which is calculated as the square root of the sum of squares of the difference between the correct answer rate for each the 180 pairs of data and the obtained as the result of the modeling. The smaller values, the better. Though table 2 P00 is the modeling error when modeling with P00, the value of N, A, and B are the correct answer rate when modeling with the parameter values shown in such ikichi, kyoku, sabun, kohia. And the value of best match is the modeling error when the value of NAB are used. This result confirms that the modeling error of the best match, is reduced compared to the table 2 P00. It is presumed that the participants who have a higher correct answer rate because of the placebo effect are able to demonstrate their full potential. This is because something that is normally guarded by ikichi is released. The case of the participant whose correct answer rate is lower because of the placebo effect, it is presumed that they become overly conscious with the equipment installed. These are the conscious guard that suppresses their true potential. In this study, the conscious guard is well controlled by ikichi. This part. Moreover, it is confirmed that people with bad memory can be modeled with a kyoku value than 1.0 as the baseline. Conclusion. We modeled stochastic reward tasks using reinforcement learning. In contrast to human data, the result of the reinforcement learning approach shows no difference owing to the differences in the placebo effect. By appropriately adjusting the modeling parameter of profit sharing, we were able to model each individual difference pattern appropriately. In the future, we intend to use deep reinforcement learning to achieve modeling with higher goodness of fit. Thank you for your attention.
We will proceed with the questions. If anyone in the audience has further questions, please raise your hand. Okay, this concludes the presentation of this blog and the day. That's thanks to all presenters and to all the members of the audience. Activities will continue tomorrow and the specific time. Thank you.
Thank you.